Good morning, Applied Physics students. This is Mrs. Krumscharter. For Chapter 4, Section 4, which is titled Acceleration, I'd like you to read it. As you're reading it, you might choose to kind of pause and listen to these notes as you go along. So Section 4.4 is titled Acceleration. And again, this is typically a term that you have some familiarity with, okay? When we're talking about acceleration, we're talking about the fact that we can change our state of motion of an object by, and again, there are several different ways we can change the state of motion of an object. By changing its speed, we can also change its direction. Okay. Or changing both. Okay, so by changing both the speed and the direction. All of these are changes in velocity. So if you kind of remember when we took some notes on that, it looked very much the same, okay? Because these were all changes in velocity. If we change our speed, if we change our direction, or we change both, we are changing the velocity. So acceleration is defined as the rate at which velocity is changing. Again, acceleration is something that you can calculate. By dividing the change in velocity by the time. So that's kind of how you calculate it in words. As an equation for calculating acceleration, A equals our change in velocity, delta V, divided by our time interval, delta T. So A equals delta V over delta T. Remember, the delta means change. So again, you might be asked to use this information to solve for some different things. So we know we have acceleration equals our change in velocity over our change in time. If we're asked to calculate for our change in time, it's going to be our change in velocity divided by our acceleration. And if we're asked to solve for our change in velocity, it's our acceleration times our change in time. Again, as we continue to talk, remember we're still talking about acceleration here. Okay. The important idea for acceleration is this idea of change. Something is changing, either our velocity or our direction. So acceleration can be increases or decreases in our speed. Right? Those are both accelerations in terms of science. Now, typically, if it's an increase in our speed, we typically refer to that as an acceleration. You're pretty comfortable with that. But typically, when it's decreases in speed, we tend to call that a deceleration. So we want to take a look at the page 51 think question. Which says, suppose a car moving in a straight line steadily increases its speed each second. First from 35 to 40 kilometers per hour, then from 40 to 45 kilometers per hour, then from 45 to 50 kilometers per hour. What is its acceleration? So this problem is asking us, okay, again, they're story problems, so I like to pull information out. It's asking me to calculate the acceleration. That's that very last sentence. We know that it's moving in a straight line. It tells us that. And it tells us, okay, that our initial velocity is 35 kilometers per hour. And our second velocity is 40 kilometers per hour. And that the change in time for that was 1 second. Then the third velocity is 40 kilometers per hour. The fourth velocity they gave us was 45 kilometers per hour. And that the change in time for that was also 1 second. The fifth velocity they give us is 45 kilometers per hour. And our final velocity is 50 kilometers per hour. And that the change in time of that was also 1 second. So to figure out our acceleration, our equation is our change in velocity over our change in time. Notice that each time, okay, our velocity has changed here. Each time it's changing by 5 kilometers per hour. So our change of velocity is 5 kilometers per hour. Each time the time interval is 1 second. So that gives us an acceleration of 5 kilometers per hour seconds. So that is that page 51 think question. So again, we're still talking about acceleration here, and so I have a statement that I want you to say whether it's true or false. Okay. Acceleration is simply an increase in speed. So take a moment to think about that. Is that statement 100% true? 100% false? Like, what is that statement? Is the only way to have an acceleration is an increase in speed? I hope you said false. Right? because acceleration is actually any change in speed, direction, or both. Okay, which kind of makes our statement false. All right, we want to take a look at a problem. Find the acceleration of a car that goes from rest to 100 kilometers per hour in 10 seconds. Again, I like to pull out the information. So I know that my initial velocity is 0 kilometers per hour because it's at rest. My final velocity is 100 kilometers per hour. And I know that my time interval is 10 seconds. So my equation is change in velocity over change in time. My change in velocity is 100 kilometers per hour minus 0 kilometers per hour divided by the 10 seconds, which is 100 kilometers per hour divided by 10. 100 divided by 10 is 10. So my answer is 10 kilometers per hour seconds. And because it's acceleration and because velocity has a direction, we're just going to say its direction here is forward. It's accelerating 10 kilometers per hour per second. So we can have accelerations when we have a change in direction. So acceleration also applies for changes in direction. For example, when you go around a curve at constant speed, you are accelerating. Because of the change in direction. And you often feel that if you're riding in a car because you kind of feel your body kind of pulling towards the outside of that curve. That's acceleration. Acceleration is a vector quantity. Remember, that means that it requires a direction. So a good example of that is if we take a look at figure 4.7 on page 52 in your textbook. I'm going to kind of use little stick figures here. So there's kind of a road and then a cliff, and there's a car, and its velocity is to the right and its acceleration is to the right. Okay, so that's kind of car number one. And in this case, you accelerate in the direction of your velocity, right? Because they're both pointing the same way. So that means that this car is speeding up. Next, we have a car. Its velocity is to the right, so it's still moving to the right, but the acceleration is to the left. Okay. So now we accelerate opposite the direction of our velocity. Which means, okay, that the car is slowing down. The last picture is the car's gone over the cliff. My velocity is kind of downwards. My acceleration is straight down. Here we are accelerating at an angle to our velocity, which means we have a direction change. So again, acceleration can happen from changes in direction. This third one is an example of that. Okay, our acceleration is downward, and we're changing our direction of movement. Acceleration also happens from a change in speed, and this is again probably the type of acceleration that you're more familiar with. When our motion is in a straight line, then our speed and velocity can be kind of used interchangeably. Meaning, because you're in a straight line and your direction isn't changing, then remember speed and velocity become very similar, because the only difference between speed and velocity is speed is scalar, doesn't have a direction, and velocity does. So when our direction isn't changing, realistically speed and velocity are pretty much the same thing. In which case we have an equation that is that acceleration, and again this is when we're talking about being in a straight line, okay, is equal to our change in speed, so delta S, over our time interval, which is our delta T. Okay, so when we're moving in a straight line. So if we take a look at a problem that involves this, what is the acceleration of a mechanical part that moves from 0 to 10 meters per second in a time interval in a time of 1 second. So our acceleration equation is our change in velocity over change in time. Our change in velocity is 10 meters per second minus 0 meters per second divided by our time interval, which is 1 second. So this is 10 meters per second over a second, which gives us 10 meters per second squared. So if we take a look at the page 52 think question, in 5 seconds, a car moving in a straight line increases its speed from 50 kilometers per hour to 65 kilometers per hour, while a truck goes from rest to 15 kilometers per hour in a straight line. Which undergoes greater acceleration? What is the acceleration of each vehicle? So first we have our car. And again, the change in time is 5 seconds. They tell us it's in a straight line. Our first velocity is 50 kilometers per hour. Our second velocity of the car is 65 kilometers per hour. So acceleration, again, is our change in velocity over our change in time. So we have 65 kilometers per hour minus the 50 kilometers per hour divided by 5 seconds, which is 15 kilometers per hour in 5 seconds. 15 divided by 5 is 3, so it's 3 kilometers per hour second. So then if we take a look at the truck, it's also in a time of 5 seconds. It also told us it was in a straight line. Here our initial velocity is at rest, which is 0. Our final velocity is 15. So our acceleration is our change in velocity over our change in time. So we have 15 kilometers per hour minus the 0 kilometers per hour divided by the 5 seconds that it takes to do that, which gives us 15 kilometers per hour in 5 seconds. 15 divided by 5 is, once again, 3, so 3 kilometers per hour times second. So notice then the last two questions were, what is the acceleration of each vehicle, which we calculated just now, and which undergoes greater acceleration? Okay, the car and the truck undergo the same acceleration. Because they both accelerate at 3 kilometers per hour per second. Okay, so acceleration doesn't have anything to do with how fast the vehicle is going at the end of its acceleration. It's just asking how much did that velocity change in the time interval. So that brings us to the end of Chapter 4, Section 4. Have a great day. I'll talk to you tomorrow.